Thank you very much for the introduction, and thank you for the invitation. It would have been nice to be in Saint-Étienne to see everyone. This presentation will be about what I call here these complex nanostructured surfaces. So these are basically disordered assemblies of nanoparticles that are deposited on a layered substrate or incorporated in a layered medium. And in particular, what is interesting with those systems is to understand how the structure can be engineered to control the scattering properties of the surface. And these can have interesting applications, as I will try to show. So as was said during the introduction, I'm currently working at the Institut Lumière Matière in Lyon, but most of this research here was developed at Laboratoire Photonique Numérique et Nanosciences, LP2N in Bordeaux, where I was working before. And for this, I would like to acknowledge a few people, especially the group leader in LP2N, in which I was working, Philippe Lalanne. I'd like to acknowledge also Adrien Agreda and Armel Pitlet, who are doing a postdoc in the group, and some colleagues between LP2N and INRIA, Bordeaux Sud-Ouest, Xavier Granier, Romain Pakanowski, and Pascal Barla. The three of them are experts in computer graphics, so there will be a small part about computer graphics in this presentation. And also, I would like to thank Jean-Paul Hugonin, without whom it would have been difficult to do all the modeling, since he developed many very useful numerical codes to solve multiple scattering problems. And finally, some financial support, also the ANR and the University of Bordeaux, who helped in funding those. So this is the content of this talk. There will be 4 parts. I will start with an introduction on the topic. The first part will be about wave scattering by rough surfaces. I think it's a good starting point. It will allow me to introduce some basic notions, some concepts, and also to discuss very rapidly the main models that have been developed to solve this problem. In the second part, I will discuss more specifically those complex resonant nanostructures that are being studied since the past 2 decades and that are very interesting for many different applications. I will try to give a brief overview of those applications and why those structures are actually interesting. In the third part, that will be the most technical, I would say, I will discuss more specifically the modeling of those structures. So in particular, I will try to give some insight on how we can engineer the particles and the disorder to obtain some specific functionalities. And in the last part, I will show an example of application of those complex nanostructures that will be about the design of visual appearance. And we will see that those structures, those surfaces can really create new visual effects that could be interesting for many branches of visual art. So let me start with the first part on wave scattering by rough surfaces. So this is a very classical problem for many kinds of waves. It can be in acoustics, optics, microwaves, radio waves, and in many fields of applications, obviously. So the problem is the following. Essentially, we have a surface, we send a wave on this surface, and we are interested in understanding how the surface will reflect light, or it can be also in transmission, but in this presentation, it will be mostly about reflection. So surface roughness is basically a random variation of height on the surface, and this random variation of height will scatter light. So basically, when you have a surface that is perfectly flat, the light will be reflected specularly. So this is just like a mirror or a piece of glass. And when you increase the surface roughness, you expect to have more light that will be spread in all directions of space. Eventually, when the surface will be extremely rough, as shown on this figure, then you expect to lose the specular property, and light will be scattered really in all directions. The surface will become nearly Lambertian, I would say. So as I was saying, there are many fields of applications for that, and one of the obvious and most popular field of application is in Earth and planetary sciences. In this case, you really want to infer some information about the topology of a surface that you don't know from remote measurements. So essentially, you send a signal on the surface, and then you collect part of the reflected signal, and you try to guess to obtain some information on the surface. So obviously, this is very important for astronomy, geophysics, oceanography, and so on. This kind of problem is also interesting for material science. So if you want to study if you want to get some information on the texture on a material, for instance, you can use this kind of approach as well. But you can think of the problem the other way around. That is, you may want to try to engineer the surface texture to obtain some specific properties. So that could be, for instance, in acoustics, to divert a sound wave on the sides, for instance, or to avoid some specular reflection, or in optics or in radar. This could be interesting as well. And the last field of application that I will discuss a bit later again is in computer graphics. In computer graphics, basically you try to create synthetic images of macroscopic objects in realistic environments. And obviously, the visual appearance of an object depends very much on the surface properties. So in this case, knowing how the surface roughness is impacting the scattering properties is very important. So there has been a lot of development on the topic in this community. So as I was saying, this is a very long-standing topic. I will not enter details, theoretical details on the topic in this presentation because I don't have time. But you have many really excellent textbooks on the subject that I warmly recommend. So let's start from a practical example. I have here an incident beam, a light beam incident on a rough metallic surface that you can see here. This is a wave, obviously. So the beam arrives on the surface, and depending on the place where it will be reflected, you have parts of the light that will spread along all directions in space. And because this is a wave, you create some wave interference, and this will create a speckle. The speckle is something that is very well known, and you've all experienced that at some point. You have it if you shine a laser pointer on a piece of paper, for instance. These are these variations, these bright and dark spots of light that can appear, and that are due directly to the interference of light on these disordered systems. So a speckle is very specific to a specific disordered system. That is, if I illuminate here a different part of the sample, that is a different rough surface, I will get a very different speckle pattern. So in the end, what is interesting to us is not really to understand what is the speckle pattern for a specific disorder realizations, but it's more to understand how the statistical properties of the scattered field are related to the statistical properties of the surface topology. And this is what people have been looking at. When I talk about the statistical properties of the scattered field, I may be interested in the average intensity, for instance, and this is what we will look at. But you could also look at the correlation of the intensity, of the speckle intensity with the angle, or the spectral correlation of the intensity in the system. And the statistical properties of the surface can be the statistics of height, of the roughness, but it can be also the spatial correlation okay, lateral coloration in the plane of the surface. So again, there has been a lot of work on that. The quantity that will be interesting for us, it's the so-called BRDF. It means the bidirectional reflectance distribution function. And this is a quantity that describes how, on average, a surface is redistributing the energy of an incident wave in the far field. So if I have a surface here that will be rough, okay, it's sketched here as a flat surface, but it can be rough. The BRDF will give you some information for all angles of incidence of how an incident light will be scattered in different directions. So formally, the BRDF, it has the dimension of steradians -1, and this is the ratio between the reflected radiance of the surface over an incident irradiance. So the incident irradiance, this is like the intensity of light, and the reflected radiance is a radiant flux in a certain solid angle, so in a certain direction. So this is the BRDF, and there have been many BRDF models that have been developed throughout the years, during many decades. And there are two classical BRDF models that I would like to present here. They are interesting because they really show somehow also the limitations of what is currently known. The first model is called the tangent plane approximation. It's also known as Kirchhoff approximation. And it assumes that you have a surface that is locally smooth, flat. So essentially, at each point of the surface, the curvature radius should be large compared to the wavelength. In this case, you can imagine that light is really like a ray. Okay, you can have still the phase in this way, but it's like a ray that arrives on the surface and that will be specularly reflected by the surface. The reflection coefficient of this light will be given by the Fresnel equations. So this is just the equation that describe the reflection and the refraction at an interface. And this is very intuitive because you understand that when you increase the roughness or when you have some random tilts of the surface, then the specular peak will become broader and broader. So this is a very intuitive model and very useful that has been developed many years ago. In the original formulation of this model, you clearly neglect multiple reflections between different parts of the surface. Okay, but there have been other models that have taken that into account. So this is the first part of the model where the surface, the typical dimensions are very large compared to the wavelengths. And the other model is called the small perturbation approximation, or also Rayleigh-Rice approximation. It's the opposite. It's where you have a flat surface with tiny variations of height. And tiny variations of height, that means that the height variations, the fluctuations, are very small compared to the wavelengths. Actually, in the previous talk, we've seen the scattering of light by very small particles. This is called Rayleigh scattering. And here, this is, let's say, the same process, except that this is for a surface. So when you will send the light on this complex surface with very small particles, with small perturbations, the incident light will polarize the small volume elements. The small volume elements will behave as small dipoles, and the dipoles will radiate the energy in all directions of space. So this is like Rayleigh scattering, but on a surface. The result is that the light is indeed scattered along all directions and with an efficiency that varies as 1 over the wavelength to the power 4. This is very typical of Rayleigh scattering, and this is actually what explains the blue color of the sky, Rayleigh scattering, and this is found also for this kind of surfaces. Also in this model, the multiple scattering usually is neglected. So light is interacting only once with the surface. It's polarizing a small volume element, and that's it. There is no interaction or multiple scattering on the surface in the original formulation. So you can see here that we have two models, one for structures that are very large compared to the wavelengths, one for structures very small compared to the wavelengths. So of course, the question is then, what can we expect when we have wavelength scale scattering elements that would be interacting together? And this is the point of this presentation. This brings me to the second part of this talk on the complex resonant nanostructure. And a good way to introduce that is to go back again to the basics. This is to consider simply the scattering of a plane wave by a particle. So this problem, a very fundamental problem, was solved rigorously by Gustav Vynck more than a century ago, at the beginning of the 20th century. So Gustav Vynck proposed a solution of Maxwell's equations, a rigorous solution of Maxwell's equations in this case, that is extremely general. The problem is the following. You have an incident wave that here is a plane wave at a given frequency or at a given wavelength with a certain polarization that arrives on spherical particles. So the exact solution exists for spherical particles or for cylinders, not for more complicated surfaces. And what I would like to show, I'm not going to show all the details of Mie theory, of course, here. But what I would like to show is that the scattering by particles with a high refractive index is very interesting for several reasons. The first reason is that the scattering efficiency is extremely high. So here on this graph, I'm showing the scattering efficiency of a particle with an index of 3.5. It's roughly the index of silicon in the near infrared range. And the scattering efficiency is defined as the ratio between the scattering cross-section over the geometrical cross-section of the particle. The scattering cross-section is a bit the superficie, the surface that is occupied by the particle in terms of scattering. So in fact, because this is a coherent process, while if you would see light just as a ray impinging on a sphere, okay, the cross section will be just the superficie of the sphere. So this would be pi r squared. And since this is a coherent process here, the actual scattering process can make that the particle is effectively much larger. So you can have a very strong interaction of light with high index particles. So here, the scattering efficiency, you can see, you have the Rayleigh regime where the size of the particle is very small compared to the wavelengths. And this is a regime where the scattering will be relatively weak. But at some frequencies, when the particle will be roughly on the order of the wavelength in size, the particle will behave like a small optical cavity that will confine light very efficiently and very efficiently scatter it. And you observe what you call what is known as Mie resonances in the system that can be extremely interesting for different applications. Now, this is just for a simple dielectric sphere, but in the past 2 or 3 decades, there have been considerable advances in nanofabrication of high-index materials that can be either using top-down techniques like e-beam lithography or bottom-up techniques that can be like colloidal chemistry, for instance. And all the different works have shown that by using a clever mix of dielectric and metallic materials together, or by engineering the shape, by creating some asymmetry of the shape of the nano objects, you can really have extremely exotic and rich optical properties despite the very small size of the object. So in this first example on the left, this is a core shell particle. You have a dielectric core and a very thin metallic shell, and that is just a few nanometers thick. And what is quite remarkable when you look at the extension spectrum is that simply by changing the thickness of this metallic shell just by a few nanometers, you can shift the resonance frequency of this particle by a few hundreds of nanometers. This is not at all intuitive, but this is quite remarkable. So you have a lot of tunability. Okay, you can have resonances in the visible and near infrared range very easily. When you create some asymmetry in the particle, like in this plasmonic nanocup, as we call it, you can make such that the particle will scatter light always in the same direction at a specific wavelength, independently of the angle of incidence of light. So this is a light bending effect. And in this silicon nanocylinders, nano PRs, you can optimize the shape as well of this PR such that the scattering will be completely forward. So in this case, you actually rely on the interference between the different Mi resonances in the particle to obtain this functionality. So again, the message here is that already at the level of one nano object, you can have a lot of interesting functionalities by playing with the different materials of the object and by playing with their shape. You can have strong scattering and you can control the directions where the light will be scattered. So usually those particles are also not studied just as one particle, but if you are interested in some applications, you try to make surfaces or materials made of such particles. So you deposit those particles on the surface. And if you use bottom-up approaches, those particles can be placed randomly on the surface. And what is interesting there is that the interaction of the particles with the interfaces of the substrate or the mutual interaction between the particles can enrich the optical properties of your surface. It can really bring new optical features. I'm giving here one example. This is a metallic nanocube that is placed on a metallo-dielectric substrate. And you have a very thin gap of dielectric of a few nanometers between the nanocube and the gold substrate. So the nanocube itself is just an object that will scatter light. There is nothing special. And the substrate itself is just like a mirror, okay, a specular mirror. So there is nothing special again. But when you place the nanocubes on top of the surface and when they have a specific dimension, you can see in the reflectance spectrum of the surface that almost all the light is absorbed at a very specific wavelength and for all angles of incidence. And this functionality, which is new, is due really to the interaction between the nanocube and the metallic substrate that is forming a hybrid mode, which is strongly absorbing light. So this is an example where the interaction of the particle with the substrate can be exploited for a new application or a new functionality. Now, those complex nanostructured surfaces are becoming really widespread in optics and photonics, and you can find in the literature many examples where they are being studied for different applications. I'm showing here 3 examples. There is a lot of activity today on using nanostructured surfaces to create colored pixels. That can be interesting for security printing, for instance, and there is some activity in Saint-Étienne on that in particular. It can be for sensing as well. So in this example, you have again those nanocubes that are placed on the substrate, and when you change the dimensions of the nanocube or when you change their density, then you can see in reflection that you have a different color that appear, and that allows you to make some kind of displays, for instance, with different colors. Another interesting and powerful application, very interesting application, is in organic LEDs. So an organic LED, it's a light source. So it's a thin film stack where you have light emitters that are incorporated in one of the layers. And these light emitters are active. So the light emitted by those emitters actually is extracted partly, and it remains confined partly by index confinement simply in the layers. So when you design, actually you can design nanostructured surfaces for extracting light and the result that is shown here is showing how the quantum efficiency can be improved when you incorporate such a disordered system there. Another topic, it's more fundamental, it's not an application, but it's on the study, fundamental study of mesoscopic phenomena. So mesoscopic phenomena, it's essentially the study of light transport and localization in disordered systems. Here in this example, this is a dielectric membrane that is perforated by holes. So the holes are playing the role of scattering elements. The light is propagating in the plane. And what the authors in this work studied was how the multiple scattering is creating some optical cavities in the system, and how we could control the density and the coupling between the different optical cavities in the system to control the transport of light. So there are many activities on those complex nanostructured surfaces, and again, the message is that those systems really contain many degrees of freedom to control the scattering and the transport of light, which can be interesting for different applications. So this brings me now to the third part on the modeling. That will be the most technical part. I will try to go slowly. I have time anyway. So let's go back to the initial problem, that is a surface that can be any surface that is scattering light. So I have an incident field or a background field that I will write EB, B for background. And this incident field arrives on the surface. The surface will scatter light due to some heterogeneities or some roughness or some particles that are placed on the roughness. And this so generates a scattered field. I define the total electric field in the system just as the sum of an incident field and a scattered field. Now, since we are interested in statistical properties, not in just one realization, but on, let's say, the average response of the system, I can write that the scattered field, I can decompose the scattered field as the sum of the average scattered field. So average over the disorder configuration, or average over the surface roughness, plus a term that fluctuates from realization to realization. So by definition, this fluctuation term, this fluctuation of the scattered field, its average is equal to 0. Okay, and this is important. Clear. So I have a total electric field, an incident field, and a scattered field that is decomposed as an average field and a fluctuating part. If I want to calculate the average intensity, then it's not the field, but the norm square of the field that I should look at. And a very simple calculation shows that looking at the average of the norm square of the electric field can be decomposed into two terms. The first term is the square norm square of the average field, average total field, and this will be called the coherent intensity, plus a term that depends only on the fluctuations of the scattered field, and this is the average of the intensity of the fluctuating scattered field. That we call also the incoherent intensity. So a bit of explanation of that. The coherent intensity, actually, if you develop this term in terms of the incident field and the average scattered field, you see that you have an interference between the incident field and the average scattered field. The coherent intensity is actually the component that will give you the specular component, the specular reflection of the surface. I do not have time to explain in detail why, but the message will be that if you want to consider the specular component of a surface, you need to look at the average field. The second part is called the incoherent intensity, and this will be related to the diffuse part. Actually, if you consider that you have a surface without any heterogeneity, without any randomness, roughness, then there will be no fluctuation of the scattered field. So this term is going to 0, and you find that the average intensity is purely specular. So this all makes sense. The incoherent or the diffuse intensity is then directly described by the fluctuation of the scattered field. And this means that the BRDF, the component that I introduced a bit earlier, could be or can be decomposed into two parts, two components: a specular part that will be evaluated from the square norm of the average field, and the diffuse component that will be evaluated by taking the difference between the average intensity and the coherent intensity, or equivalently, the difference between the average scattered intensity and the intensity of the average scattered field. Voilà. So I would like to go on just to introduce some very fundamental and classical problem to show how particles collectively can create some interesting optical features, and why the collective response of an assembly of particles constitute a degree of freedom to control light scattering. So again, this is a derivation that can be found in many textbooks that you have seen if you have studied crystallography, X-ray diffraction, for instance, or solid-state physics. So let me start by considering just one particle that is illuminated here by a plane wave, and I will look at the field scattered by this particle. I can define the scattered field in the far field by what is known as the scattering amplitude of the particle. The scattering amplitude is a quantity that describes how an incoming plane wave is scattered as an outgoing spherical wave. So simply, formally, I write that the scattered field, the field scattered here by particle J at position R in space, is the product of the scattering amplitude of this particle that relates two directions. These are the wave vectors of the incident wave and the wave vector of the scattered wave. Here, this is the incident field, the background field on particle J. And here, this is a spherical wave, exponential IKR over R. So this is very classical, and this is the definition of the scattering amplitude. Now, if I have an assembly of particles, and I suppose that the particles are not interacting together, so I will come back to this point, but basically that means that essentially the field scattered by each particle, or let's say that each particle is seeing the incident field as the source. Then I can define a scattering amplitude for this assembly of particles. That is simply the sum of the different scattering amplitudes of the different particles. And I have to add a term that accounts for the dephasing due to the different position of the particles here. So this term is an exponential. It's a phase term, where you have here the difference between the incident and the scattered wave vectors, and the scalar product with the position of the particles. Again, this is a dephasing. Since we are dealing with a coherent process, we have to take this dephasing into account. So here I have a definition of scattering amplitude, and if I want to have a scattered intensity for the system, I just need to take the norm square of this quantity. Here, because I'm considering a polarized light, I will project, or I will consider a specific incident polarization and a specific scattered polarization. So essentially, the scattered intensity will look like that. This is the square norm of this quantity there. And I can simply establish this relation where for identical particles, you will have two terms. The first term is the square norm of the scattering amplitude that will tell you how one particle is scattering light in different directions. And the second term is a term that doesn't depend on the details of the particles, but only depends on the position, the relative position on pairs of particles. You see that this term here, the dephasing, depends on the difference in position between the two particles, Rj and Rk. Now, this is the scattered intensity, and this scattered intensity for one realization will give you a speckle. Okay, the speckle is directly due to this term that is here that creates this interference. Now I write again this previous equation, and I will just take the average. So since all the particles are the same, the average will only be made on the second part, on the sum that is there. And eventually, I can write that the average cathode intensity will be the product of three terms. The first term is just the number of particles. So that means that essentially, if I increase the number of particles, then the cathode intensity will increase linearly with the number of particles. The second term is called the form factor. This is essentially the scattering diagram of one particle. This is how, if you send light on one particle, the energy will be radiated in the different directions. And a third term that will be the structure factor that describes the effect of correlation of particle pairs on the scattering. And this term is expressed as follows. This is simply the average of this quantity. And here I separate this into two terms as one plus a term that depends on the difference between two different particles in the system. So the structure factor and the form factor are very classical. They are very well known. Okay, you can find that in many textbooks. This is a very classical definition. But what is important there is really to notice that in terms of scattering of light by particles, I have shown in the first part of the second part, sorry, of this presentation, that you can engineer the shape of the particles. So you are basically playing on the form factor here of your system. But the structure factor that is related to the spatial distribution of the particles is also very important and constitutes an additional degree of freedom to control the light scattering. So in a way, the structure factor is giving a different weight to the scattering properties of the individual particles. And I will show some examples in a few minutes of that. So when presenting this small formalism here, I started by saying that we assume that each particle is being excited by the incident field. So in fact, we neglected the effect of multiple scattering, which can be very important if you have a very dense system of particles. In fact, I should have written that the field scattered by a certain particle J here is not simply the scattering amplitude times the incident field or the background field on the system, but it should be an exciting field on the particle J. And this exciting field on particle J is not only the incident field on the system, but it's also the field which is scattered by all the other particles on the particle J. Okay. So simply, this term here should be, again, the incident field on particle J plus the field scattered by all the other particles that I labeled here K on the particle J. And this field obviously depends from particle to particle. It will depend on the position of the particles, on their distance, and so on. So actually, if you incorporate this small equation here, you can see that the scattered field produced by particle J depends on the scattered field produced by particles K, by all the other particles. And this is what defines the multiple scattering problem. So essentially, this is the problem that we have to solve. Numerically, this problem can be solved rigorously using linear algebra. And I invite you to look at the literature on T-matrix methods. For instance, there is an excellent book by Mikhail Mitchenko on the topic. And actually, there is also a list of open source codes to solve a multiple scattering problem that exists that you can find on scatport.org. It's a website that is handled by Thomas Fritz in Bremen, in Germany. It's very, very useful. Numerically, we can solve a multiple scattering problem, and I will show some examples in a minute. And theoretically, we can do some things as well, but we need to do some approximations. And a classical approximation is to say that the particles will be excited not by a specific field, but the average exciting field. So in this case, we need first to calculate an average exciting field, and then we can calculate the scattered intensity. And for details, there is this excellent textbook as well that is quite technical, but that allows you to understand really all the fine details of multiple scattering problems. So coming back to our problem, we want to have a BRDF for monolayers of particles in layered media. So there has been a lot of work in the literature on the specular component, so the coherent intensity. And in our work, we use a model that has been developed by Garcia Valenzuela and his colleagues in Mexico. So essentially, what you have is a BRDF that will be made of Dirac deltas, okay, because this is specular light. So the direction of reflection is directly given by the direction of the incident light. And the reflection will be given by a reflection coefficient that takes into account the multiple scattering, so the interaction between particles. A main contribution that we have made in our group was to develop a model for the diffuse component of the BRDF, that is for the incoherent intensity. And eventually, the formula looks like that. It should remind you something that you have seen just 2 minutes ago. The BRDF can be written as the product of different terms. There is the surface density of particles. There is the first term that is the differential scattering cross-section. So it's essentially the form factor of one particle. There is the structure factor that is essentially that depends on the correlations, structural correlations in the system. And there is a last term that incorporates a correction coefficient accounting for multiple scattering process. So the originality of this formula is basically this correction coefficient. If you take it equal to 1, this is the approximation of independent scattering. But we will see that independent scattering for monolayers of particles, it has some problems of divergence in some cases. And here we introduce the correction coefficients that solve those problems and takes into account quite properly multiple scattering process. So I will show you now some comparisons between the predictions of our BRDF model and the full wave multiple scattering calculations that can be made. So these are rigorous calculations that have been made with the homemade software. So I'm considering here a simple system. It's a semi-infinite glass substrate that is supporting a disordered ensemble of silicon particles of radius 70 nanometers at a surface coverage of 10%. So this is quite a high surface coverage. It said that the particles are really close to each other. And the different panels, the different curves that you see here. On the top, you see the specular reflectance of the system. On the bottom, you see the diffuse reflectance. The different columns are for different incident angles. So this is at normal incidence. The second column is at 60 degrees in TE polarization, and the third one at 60 degrees in TM polarization. And on each curve, you have 3 curves. On each panel, you have 3 curves. You have the numerical simulations. These are the dots. You have a dashed line that is a model of independent scattering, so where we neglect the interaction between particles. And we have the black line, which is the model that incorporates multiple scattering process in the system. So you can see that already, if you look at, if you compare the different curves, we have a very good agreement between our model in general and the numerical simulations, much better than in the independent scattering approximation. So for instance, if you neglect the interaction, if you have independent scattering, you can see that the reflectance is much higher at oblique, at grazing angles. Actually, it can even diverge if you go at near 90 degrees of incidence. And the second observation is that in those systems of nanoparticles, you really have a very rich spectrum. You have some fine spectral features that appear, and that will be important for the next part that will be on visual appearance. So here there is a comparison for a slightly more complicated system. This is the same assembly of particles, except that they are placed on a silica layer and of a certain thickness, 400 nanometer thick, on top of a semi-infinite silicon substrate. So here you can see that you can imagine that you have strong interferences between the particles and the substrate. And this makes that the specular reflectance and the diffuser reflectance have spectra that are becoming extremely complicated. You can see that our model is quite accurate still, so it can reproduce quite nicely the different spectral features of the structure for both the specular reflectance and the diffuser reflectance, which is quite nice, whereas the independent scattering approximation doesn't work so well at grazing angles again. And the last comparison that we can do is to look simply at how the light is scattered in different directions. So here at a specific wavelength, and here we are comparing two different systems with the same particles, with the same density, except that we implement some short-range correlations. So P equals to 0, 1. This is a system where basically the particles are placed randomly on the surface at really random positions. There is a very small correlation in the position of the particles. And P equal to 0.5 is a situation in which the particles are strongly correlated at short distances. So essentially, it would be like the particles would repel themselves a bit. You create some minimal distance between the particles, and that creates some kind of correlation. This correlation will have a very strong impact on the scattering properties of the system via the structure factor that I presented in the previous slides. So here on this graph, I'm showing the scattering diagram of the surface. That is essentially the BRDF of the surface for a given incident angle. On the left, we have the predictions from our model. On the right, the predictions from the numerical simulations. The first observation is that we have a very good agreement, a good quantitative agreement between the model and the numerical simulations. And the second observation that is more interesting probably is the fact that if you take a system and you just engineer a bit the correlations in your system, so you move from this system to this one here, you really have a scattering diagram that is very different, very different. And we will use that in this last part to to create some new visual effects. This is an example of application of these complex nanostructured surfaces. So to introduce that, I should say that in the past 5 to 10 years, there has been a lot of activity in the photonics, plasmonics community to create surfaces with certain structural colors. So actually, in the literature, you can find really hundreds of papers on that. The basic idea is that when you have a surface and you have some scattering elements, as I introduced a bit earlier, when you change the size or the dimensions, the materials of the individual scatter, you will modify the scattering properties. And in particular, you will modify the spectrum of the scattered light. So if you take a small particle, you will have a very different spectrum than if you consider a much larger particle. So actually, when you use different particles, you could imagine that in reflection, then a surface that will be made of different types of particles will create different colors in reflection. And people in the community have looked a lot at how to optimize the dimensions and the size of the different particles on the surface to create different colors, and they could reproduce experimentally some paintings or some photographs with different colors on the sub-millimeter scales. You can see here, this is a painting of a size of about 1 millimeter. Here you have some photographs and paintings that are reproduced. The scale bars are 10 microns and 15 microns here. And this can be made using dielectric particles or metallic particles, because those can really produce a wide range of colors. Now, it's very nice to talk about colors, but we were interested more in the broader question, that is the visual appearance of the surface. So indeed, the visual appearance of an object is not just the color of the object. This is more complex. The visual appearance depends on the lighting environment. So it depends on where the light is coming from. It depends on the kind of light. Okay. It depends a lot on the shape of the object. You can have objects in which you have also multiple reflections, and this will be important for the visual appearance of the object. And it depends a lot on the weight between the specular and the diffuse components. Okay. So the specular light, as I was saying, is like a mirror. So this is what gives the glossiness of an object. And the diffuse component is what gives an object a more matte appearance. And the weight between the specular and the diffuse are obviously extremely important. On this topic of visual appearance, a bit of advertisement, I should say that there is a groupement de recherche, GDR, that is federating all the activities in France on the visual appearance of materials. That is called GDR APAMAT, and that is coordinated in Saint-Étienne. So I advise you to have a look if you don't know, if you didn't know this GDR, and if you are interested in the topic. So we wanted to know about the visual appearance of nanostructures, but clearly there was a gap between, let's say, what people could engineer at the nanoscale and the macroscopic visual appearance that is much more complex. And what we developed with our colleagues is actually the first numerical platform that is merging electromagnetic modeling at the nanoscale and computer graphics at the macroscopic scale to predict quantitatively the visual appearance of macroscopic objects that would be covered by nanostructured surfaces. And why this is interesting? Because we can simply, very simply, change the parameters at the nanoscale and observe at the macroscopic scale via synthetic images how those changing impact the visual appearance of the object. And we have found some very interesting visual effects that I will present in the last minutes of this presentation. Here, this is an example of what we can do. You have 4 synthetic images of a common object. This is a car, but our objective is not to sell paint for cars. Okay, it's just an example of visual appearance. So when you have a surface that is not covered by particles, you have essentially a very black object with a strong specular component. If you would cover here this object by small silver particles at a certain density, you would get some diffuse color, a gray color that would appear. That is a bit like if you would create some roughness and give a bit more of diffuse light in the system. So it would be like a bit random roughness on the surface. But what is more interesting and what we try to exploit in our work is what happens when we create a structural correlated disorder in the system. So we engineer the position of the particles in the system. And as I will show, engineering structural correlations is creating all these very nice colors that are appearing out of the gray on this surface. And if we create a layered substrate, you can either create a new colors and new appearances, new visual effects that we understand. So very briefly, the strategy for the predictive rendering it's quite simple. We start from solving the electromagnetic problem at the level of a single scatterer. It can be a single scatterer that is on top of a layered substrate, and we calculate in practice the scattering amplitude of this object to know how the light will be scattered. I told you about the scattering amplitude previously. Then we have our approximate BRDF model that allows us to predict how an infinitely large surface made of such nanoparticles at a certain density with a certain correlation will reflect light. So we have the BRDF, the complete BRDF at all wavelengths, all incident angles. And then we incorporate this BRDF model in a multispectral rendering engine to generate some synthetic images of macroscopic objects in realistic environments. So in brief, the system that we considered in this work are spherical particles in air that are deposited on a layered substrate. And we try to understand how changing the size or the composition of the particles, the composition of the substrate, or the density and the correlations in the position of the particles are affecting the visual appearance. So the first step is to look at just the engineering of the particle. And this is basically what everyone has done so far, changing the material of the particle or the size of the particle. Here you can see that different materials and different size of particles will, a priori, generate different colors in reflection. This is again what people have studied so far in the works on structural colors with these surfaces. What was not known really was the fact that the specular light and the diffuse light can have very different colors and very different behaviors actually. So here we're looking at the colors that are created by spherical silicon particles of two different sizes and at different densities and different incident angles. On the top, you have the diffuse component, and you see that the diffuse component, the color is always roughly the same for all incident angles and all densities. So the driving parameter here is really the size of the particle that is creating a different spectrum and creating a different color. But more interestingly, the specular component depends a lot, not only on the incident angle. So this is like a thin film interference, but it depends also a lot on the density of particles. You can see that changing the density of particles is creating different colors. So that means that essentially we have a way to control almost independently the diffuse color and the specular color of an object. And clearly the diffuse color and the specular color are both extremely important for the visual appearance. Here I'm showing some synthetic images of a macroscopic object. It's a sphere that will be covered by such a nanostructured surface. On the left, you have the predictions only for the diffuse part. In the middle, only for the specular part. So you see that here you have a surface that is completely matte. There is no reflection, no direct reflection. You cannot see the chessboard here. Here, this is specular light, so this behaves just like a mirror, and you can see that you have some colors that is different from diffuse light, and the real visual appearance of the object will be the sum of the two with the diffuse and the specular components. So this shows clearly that all the fine details about the specular and the diffuse component are really essential for visual appearance. Then, okay, I have 2 minutes left. Then we also looked at engineering the substrate. I will skip this part, but basically the message is that when you have particles on a layered substrate and you increase the thickness of this substrate by a certain amount, you go from 0 nanometers. So here the particle is directly on a silicon substrate, and here you create a spacing of 400 nanometers. You create some angle-dependent diffuse colors that are very different from the thin film iridescence that you know. So this is what we call the diffuse iridescence. That is a visual effect that was not reported to date to our knowledge, and that is really specific of these disordered systems. The last example that I want to show and that I find quite impressive is the effect of structural correlations. So again, previously I told you about the structure factor, the fact that the structure factor is really modifying the cathode diagram of a surface in quite a spectacular way. So if you go from a completely random system to a system where you have short-range correlations, the scattering diagram will go from something that is quite uniform to something that is very peaked angularly. And in particular, when you have a strong short-range correlations, you see that you have a suppression of the diffuse intensity around the direction of specular reflection. And you have a high intensity lobe that appears at larger angles there. And the position of this lobe depends on the wavelength of interest, whereas the suppression of the diffuse intensity occurs for all wavelengths. In terms of visual appearance, this is very interesting because simply by changing the correlations, the short-range correlations in your system, so you keep the same particles at the same density, but you just rearrange the particles together, you can go from a system, from an object that looks gray, so with no specific color, nothing very special, quite common, to a visual appearance that is extremely colorful, that looks like a bit of a rainbow on the object, where you have indeed a suppression of the diffuse intensity here near the specular direction, and some colors that appear, some bright and vivid colors that appear on the sides. So here, this is just a synthetic image for a given object in a given scene for a given illumination. But what is even more impressive, I would say, is to see what would happen when you have an object and you turn around it. So here, this is what we call the speed shape object. It looks like a futurist car in a way. This object is illuminated by a light source that is just behind you, okay? And we will rotate around the object. This is a video. I hope you can see it quite clearly. But you can see here that the appearance of the object depends very much on the viewing angle, and this creates this optical appearance that is not common at all. It's quite unexpected. When you are behind the object becomes completely dark, while it's very bright and colorful when you are just in front of the object. And we think that this is not a visual effect that has been observed so far, and that is very specific of these complex nanostructured surfaces. So this brings me to the end of my presentation. I was a bit long. I'm sorry about that. I tried to convince you that these complex nanostructured surfaces are very interesting to steer or to control the scattering of light by surfaces. Again, you have different degrees of freedom that you can exploit. You can engineer the shape and the size of the particles or the material of the particles themselves. You can engineer the layered medium in which the particles are placed, and you can also exploit structural correlations in the position of the particles to control the directivity and the spectrum of the reflected light. This, we think, can have interesting applications for the visual appearance design, and we will continue to investigate that with our colleagues that I would like to thank again, and thank you very much for your attention.